Emission spectroscopy is a method of measuring light-matter interactions. An emission spectrum is the plot of emission intensity versus wavelength. Emission intensity is not the number of photons emitted at each wavelength, but is proportional to the number of photons emitted. Emission intensity depends on the properties of the dye, specifically the molecular composition. As you can see, green dye and red dye have different molecular compositions.
The blue line is the emission spectrum for our green dye, and the green line is the emission spectrum for red dye. As you can see, the emission intensities at different wavelengths for the green and red dyes are different, so emission intensity depends on molecular composition. Molecular composition determines the relative energy levels of the electrons and how many different energy levels electrons can exist at. Excited electrons at different energy levels emit photons at different wavelengths. Also, the more energy levels present for an electron, the more possible transitions between energy levels are present. These different transitions correspond to emitted photons of different wavelengths, and the more photons that are emitted at a wavelength, the higher the emission intensity at that wavelength. In conclusion, molecular composition determines which wavelengths of photons are emitted from a substance and the relative abundance of photons emitted at each wavelength.
Here, substance 1 is similar to the green dye and substance 2 is similar to the red dye. The green dye emits photons at a higher intensity than the red dye. Additionally, lambda max for green dye is lower than lambda max for red dye. This means that the photons that the green dye emits are of higher energy. Based on these observations, we can say that the green dye has energy levels that are farther apart than the red dye.
Here's an analogy for electron transitions. Shubhangi is the electron. The ground is the ground state of an electron. The table and chair are different possible energy levels for the electron to exist at. The higher the electron is off the ground, the more energy it has. If the electron is excited at the highest energy level, the table, it can relax straight to the ground and emit a photon of high energy and low wavelength. However, the electron can also first relax to the chair energy level, emitting a photon of lower energy and higher wavelength, and then relax from the chair energy level to the ground energy level, emitting another photon of medium energy and medium wavelength because the chair is closer to the table than the ground.
Emission intensity also depends on energy input. If there is more energy inputted, then more electrons are excited and there is a greater energy of light emitted. This will cause the number of photons emitted to increase at each possible wavelength for the specific molecule, which will cause the emission intensity to increase because emission intensity is proportional to the number of photons emitted at a wavelength. In the 1-to-1 mixture, which is the red line, the green dye emits photons that can be absorbed by the red dye. This simulates an increase in energy input for red dye, which increases the emission intensity of the red dye in the mixture compared to the isolated red dye, which is the green line.